Hello everyone, my name is Stefan, and now that you are comfortable navigating GNU Radio, let's delve into foundational concepts of frequency, gain, and filters, the key elements behind the AM receiver you built in previous lectures. As you will soon discover, filters are central to almost every type of radio you will create, making it crucial to understand how they work. In physics, frequency is defined as the number of oscillations of a periodic event per unit of a time. A periodic event is any action that repeats with consistent timing. Frequency is measured in hertz, Hz, where 1 hertz equals 1 cycle per second. Frequency isn't tied to any specific type of event, it is a universal property of various phenomena. For instance, frequency is integral to the radio stations you tune into, your Wi-Fi router or mobile phone specifications, the speed of your computer processors, often measured in megahertz, MHz, or gigahertz, GHz. The audible spectrum, the range of frequencies humans can typically hear, spans from 20 Hz to 20 kHz. While this range varies with factors like age and exposure to loud noise, like heavy metal concerts, it gives a broad framework for understanding sound frequencies. We have the low frequencies, which produce deep, rumbling sounds. Mid-range frequencies are where the most everyday sounds and human speech occur. High frequencies, treble, create sharp, piercing tones. Frequencies outside this range will fall into two categories. The first is subsonic and ultrasonic. Subsonic sounds below 20 Hz, too low for humans to hear, and ultrasonic sounds above 20 kHz, audible to animals like dogs but not humans. Understanding sound frequency gives an intuitive way to grasp radio wave frequency, as many of the same principles apply. For example, just as we filter out unwanted sounds to focus on a specific conversations, radios filter signals to isolate a specific frequency channel. Let's explore frequency by creating a simple audio tone. GNU Radio treats audio data just like any other numerical data, so even though we are working with sound, it is effectively processing a stream of numbers. For this exercise, we will use GNU Radio to generate and play 500 Hz tone, providing a practical introduction to signal generation. First, we will need to create a new flow graph. In order to do that, we will open GNU Radio Companion and click on File, New Key to Graphical User Interface, the first option here. Click on it, and here we are. And we will need to add a signal source block. We will place signal source block in the workspace. We will configure the block's properties. The output type is going to be float. The frequency is going to be 500, and the amplitude is going to be 0.1. This block generates a stream of floating point numbers representing a synthetic 500 Hz signal. Now we will add audio sync block. We will drag and drop audio sync block into workspace. We will connect the output of the signal source to the input of the audio sync. And if we are using virtual machine, mostly in virtual machines, you need to set a device name property of the audio sync to sysdefault to ensure proper audio output. But if you are still getting the output without this option, this may compromise your output settings if you are even on virtual machine. So in my case, I will not change it. And we will save our flow graph. as single 500 Hz tone. Save it. And now we will run the flow graph by clicking the play button. You should hear a continuous 500 Hz tone, a mid-range sound according to the audible spectrum in here. The tone isn't practically low-pitched like bass or high-pitched treble, but comfortably in between. If you don't hear anything, ensure your speakers or headphones are properly connected. Use headphones for better audio clarity. On a virtual machine, double-check the AudioSync's device name property. This hands-on experience demonstrates how audio signals can be represented numerically and generated synthetically. It also provides a starting point for understanding frequency through direct experience. In the next section, we will build on this by exploring how to combine and manipulate these signals to create more complex audio patterns.